Okay, good morning, welcome to
MinuteMath114.
I mean, good afternoon. I wasn't going to do this one today, but it's such a cool problem. So even though we just came back from our vacation today and we got up at 5 in the morning, we're going to try to do this super hard geometry problem. You excited?
Yeah.
And unfortunately I had to start over once because I wrote radius instead of side length. But you ready for the problem?
Yeah.
A square of side length 2, so the square has side length 2, and a circle share the same center. Okay, so you got a circle right on top of a square. Alright?
Yeah.
The total area of the regions outside the circle and inside the square is equal to the total area of the regions outside the square and inside the circle. What is the radius of the circle? Okay? So this is a complicated sounding problem, but it's actually not too sneaky if you take your time.
So,
what are those regions?
these are the regions outside the circle and inside the square.
These are the regions outside the circle and inside the square. Now hold on one second. What can you tell me about those regions?
They're all supposed to be equal.
They're all, well, okay, so they're all supposed to be equal. Why is that, do you think? Why are those four regions all equal to each other?
Because the circle's supposed to be even.
The circle's supposed to be a perfect circle, and I didn't quite do that right. So we should have a nice piece of symmetry here. Like if this, and when it chops off that corner, kind of, it should be exactly the same as chopping off these, because the circle, the center of the circle and the center of the square are the same. Okay. Now what about the regions that are outside the square and inside the circle? What can you tell me about those?
Well, they're equal to the regions the blue regions. And they're all the same too, since the
they're all the same too, but what do you mean they're equal to the blue regions?
Well, it says the area of the regions outside the circle and inside the square is equal to the regions.
Okay. So the total area, filling over here too. Alright, so you notice that these red regions all have the same area, again by symmetry. And it says the sum of these areas that's outside the square is equal to the sum of the areas that are inside the square, but outside the circle. Okay? So what do you think that implies? There's a really interesting geometric idea here. What do you think that means?
Well, the distance, since the side length is 2, this distance is also 2.
Okay, that's right. That's good. The distance across the square is 2, because the height is 2, because that's what it means to be a square.
Yeah. If we chop off the red regions, then the diameter would be 2.
Oh, well, not quite, because you would still have a diameter going from here to here.
Yeah.
So we're not too sure about what the diameter of this circle is. We're not sure, but there's something else that's really sneaky to see about the red and blue regions. Can you notice anything about them? From the fact that you said these are all equal, and these are all equal, and they have the same sum.
If we take them off and put them on here, it would become a square.
Okay, that's a very interesting observation. Why can I take this region off and stick it in there, kind of mash it up, rearrange it, and stick it in there?
Because they're equal.
They're
Since
equal.
four of these is 4 of these, so you can just divide by 4.
Okay, so I could cut these off with a pair of scissors, somehow rearrange them like they were putty, but keep the area the same, and I would now form a square. So what does that tell me about the area of the circle?
It's the same as the area of the square.
Okay, so what is the equation for the area of a circle?
It's pi r squared.
So we have pi r squared equals 4, right? That's the area of the square. So what does r squared equal?
Well, it's 4 over pi.
So what does r equal now? Haha.
It's the square root of 4 over pi.
Square root of 4 over pi. Do you know how to simplify that a little bit? This is a kind of a complicated one, but there's one little thing we could do to simplify it.
Well, it's 2 times the square root of 1 pi.
That's exactly right. Or that's a good way to say it. I'll write it as 2 over the square root of pi. That's pretty cool. That is pretty cool. So the radius of the circle is 2 over the square root of pi.
That's an unusual radius.
That is an unusual radius. This is a cool problem. By the way, only 1 in 5 people got this right, and those are people who actually knew a little bit about geometry.
Yeah.
This is a cool problem, though. I wanted to show you so you can sort of mush the circle to fit it inside the square. The areas are the same, and then it's just a simple formula like that. Awesome. Awesome job, sweetie. Awesome job.